Welcome back, everyone. In this segment, we will continue our discussion about related rates and solve some of the more complex type of problems. So in the last segment, we already started our discussion and we understand, in these problems, things are changing as time goes by. Typically, they give us one rate of change, such as dy dt in a given situation, and they may ask us for another rate of change, such as dx dt or dv dt, right? And typically for these questions, here are some good strategies that you can follow. So always I would say start with a figure, extract the given information from the problem, assign variables for the unknowns, just like your typical word problems, right? But then don't forget for these questions that the derivative is always taken with respect to the time variable. So if something is changing as time goes by, you're going to write that as a derivative with respect to t. And also make sure you write down the goal. What are we trying to find here? And write that typically is going to be a rate of change. So write that as a derivative. And it's important to write an equation that relates all the variables. If they gave you the x dt, they want dv dt. How are you going to get one from the other, right? You need an equation that relates x and v, so write that down. And then typically you're going to differentiate both sides of that equation with respect to time. And keep in mind, if something does not change over time, that is a constant, and that's a value you can plug in early into your equation. On the other hand, if something is changing as time goes by, that is a variable and not a constant. So do not plug in its value, even if it may be given to you in the problem, do not plug that in early on. And what I mean by that is don't plug it in until after you have differentiated both sides with respect to the time variable. And we'll see all about these tips and techniques in our next few examples. So let's take a look at one of those. All right, let's see. Here we go. All right, so for this question, I'll give you a moment to read the question first. Okay, so in this situation, we have a plane that is approaching towards a radar tracking station, and the plane is flying at a constant altitude of 6. So notice that altitude does not change as time goes by, so that I can put in there as a constant. On the other hand, the distance that the plane is away from the radar tracking station, that horizontal distance, of course it changes as time goes by. So I'm calling that distance x, and the direct distance between the radar tracking station and the plane, I'm calling that s. And they're saying that, right, s is the distance between the two, and it's decreasing at a rate of 400 miles per hour at the moment when s is 10 miles. The question is, what is the speed of the plane? Think of it as at what rate is distance x changing. The rate of change of x, and speed will be the absolute value of that rate of change, dx dt. So the goal is to find dx dt and write down the given related rate. So what's given here is s is decreasing at a rate of 400 miles per hour. So that they gave us the rate at which s is changing, that's ds dt, and because it's decreasing, it'll be negative 400 miles per hour. And so we want to find dx dt. Ds dt is given at the moment when s equals 10 miles. And then it's always helpful to write an equation that relates to variables, so something that relates x, s, and this constant as well. This situation is always a triangle. No matter how close the plane is towards a radar tracking station, at any given moment, you have a right triangle being formed, right? No matter where the plane is, there's a right triangle that looks like this. So let's use the equation that relates the sides of a right triangle using the Pythagorean theorem. So sum of the square of the legs equals the square of the hypotenuse. So x squared plus 6 squared equals s squared. That is going to be our equation there. And at this point, what do we do with this equation? Do you remember? Yes, if you said differentiate both sides with respect to time, you were correct. So 2x dx dt is the derivative of the first term. The constant 6 squared is just 36. Its derivative is 0. And s squared is 2s ds dt. So that's the derivative of the right hand side. So we have 2x dx dt equals 2s ds dt. At the moment, you can basically cancel the 2's, so you have even a simpler looking equation. And now it's time to plug in what's given. Notice that the SDT was given, so we're going to go ahead and plug the SDT in here. S is given, right? We are trying to find the XDT, so this is fine to keep, but it looks like we also need to know what X is. And to find what X is, we're going to need to use this equation once more, because they said at the moment when S is 10, we can figure out at that moment what X will be, and from there we can plug it in here for X, and then the rest is already given, and we'll be able to solve for dx dt. So let's first of all figure out X. So S is given 10. The SDT was given negative 400. Again, now we're left to figure out what X is, and there we can find our equation. So since x squared plus 6 squared equals s squared, and s is 10, go ahead and plug 10 squared here, which will be 100, and subtract 36. So that way you can solve for X. So 100 minus 36 equals x squared. That means x squared is 64, and X is positive 8. Since it represents a length, we cannot choose plus or minus 8, only the positive 8 is selected. Okay, now that we have X, we're almost ready to finish the question. Plug it back in over here. So it'll be 8 times dx dt equals 10 times negative 400, which is negative 4,000. And dx dt will be divide both sides by 8. So let's do that. Divide both sides by 8. So we're going to have negative 4,000 divided by 8. And that turns out to be negative 500 miles per hour. And it's negative, it should make sense because that distance was decreasing as the plane is approaching towards the radar tracking station. But because this problem asks for speed, it happens to be the absolute value of rate of change, so it'll be 500. But just I want you to be aware that in the future, I will usually want you to leave the answer with the sign preceding it, whether it's positive or negative. That will be an important part of your question. So please make sure to get into the habit of reporting whether or not your rate of change is positive or negative. Okay, so let's do another problem now involving distance rate questions. And it's always a good idea if you watch the video and step by step, can you stop it now and I give you the templates, right, where the solution is not filled in, and can you redo the whole problem now without looking at the video, and that way you have truly learned it, I think. All right, so another distance rate question. In this situation, we have two planes converging towards a point, and they're flying at the same altitude at right angles towards each other. So plane B is moving in that direction, and plane A is moving in that direction. So they're going towards each other at right angles. And we know the rate of change. A is moving at a rate of 300 miles per hour and B at a rate of 450 miles per hour. At what rate is the distance between them closing when A is 250 and B is 400 miles away from the intersection? So here I'm letting X be how far A is away from the intersection, and Y represent how far B is away from the intersection, and I'm using Z to represent the direct distance between them. And they want to know at what rate is the distance between them closing or changing. So they really want to know dz dt, right, at the rate at which the z is changing, because first it was that, then it's this, then it's this, so it's changing clearly as time goes by. So at what rate is z changing? So dz dt will be determined. And so let's write down then the goal is to determine dz dt. And what is given to us in the problem? Okay, a bunch of things, right? For example, we were given dx dt, that's the rate at which A is moving. That was negative 300. Negative because that distance is shrinking as time goes by, right? Distance to the intersection is getting smaller. So dx dt is negative 300. Similarly, dy dt is, that's the rate at which B was moving. That's 450 miles per hour. So negative 450 is dy dt. And these are happening at the moment when A is 250 away. So x is equal to 250. And B is 400 away, so Y is equal to 400. So all of that is given to us. And now our job is to determine dz dt. So to relate x, y, and z, again, we have a right triangle forming here at any given moment in time as these planes are flying at right angles. So we can use the Pythagorean theorem. So here we're going to have x squared plus y squared equals z squared. That's the equation that relates the variables. So what do you do with this equation, right? As is typical now, you have probably formed the habit of, okay, you get your equation, differentiate with respect to time. That's the only way we're going to get dx dt, dz dt, etc. from this equation. And do not plug in 250 and 400 just yet, because then you would lose your equation. There would be nothing to differentiate, right? And x and y are changing as time goes by. So then they are not constants throughout. So you cannot plug in those constants early. Plug in after you've differentiated the equation. So we have 2x dx dt plus 2y dy dt equals 2z dz dt. That is the equation, the derivative of our equation. So at this point, you can divide both sides by 2, so all the 2's cancel out, and we have an easier looking form of our equation, in which case I'm going to start plugging the constants. So just up here we know x was 250. And the x dt was negative 300. So go ahead and start plugging them in. And y was 400. And dy dt was negative 450. So you can go ahead and put those numbers in. Okay, so 250 times negative 300 plus 400 times negative 450 equals, now ordinarily there you will put z times dz dt. We don't know what z is at the moment, but that's something we can figure out, because if you know at the moment when x is 250 and y is 400, at that same moment, can you figure out what z is using this equation? We should be able to, right? So go ahead and put 250 for x and 400 for y, and then equals, put them in, they're going to be squared, equals z squared. Solve for z. Let's see what we're getting there. So take a moment to do that, please. Okay, so if you plug in your numbers in to solve for z, it's basically going to be z equals the square root of 250 squared plus 400 squared, right? If you put the x in proper place and y in proper place and solve for z. So z turns out to be the square root of 222,500. I would suggest that you leave that as such. Don't try to round it yet. Round it in the last part of your equation. And when you come here and plug that in for z, this is what you're going to have. So z times dz dt, I put the value of z up there and kept the dz dt, which is the only unknown we have. So at this point, we're going to be able to solve this equation. So you can combine all these numbers on the left-hand side to get a single number. So if you do that, you're going to get negative 255,000. That equals the square root of this quantity times dz dt. So to solve for dz dt, you're going to have to divide by that square root. So when you do that, divide by that square root. So you have, finally, answer will be negative 540.6 miles per hour. So again, you can leave it like this. Typically, I'm going to ask you to leave the negatives or the positives as they are. But sometimes, for some tricky questions in the book, you might see something like, okay, if it says at what rate is closing, they might say it's closing at a rate of 540.6 miles per hour. So they may report the result as a positive because they're using the word closing, which already indicates that it's decreasing. But typically I'm going to ask you, at what rate is it changing in the future? So for dz/dt, go ahead and leave your negative answer in your final answer. Okay, as you can see, there is a lot of similarities from problem to problem, and it's always a good idea to go back and redo it if you were watching the video in the first place. All right, here's our next example on related rates. So this one I'm going to give you just a hint on, and you can see the solution in our Canvas website. So at 9 a.m., ship A leaves the port traveling west at 12 miles per hour. So A is going west at a rate of 12 miles per hour. And at 11 a.m., ship B leaves from the same port traveling due south at a rate of 15 miles per hour. And I'm calling the distance that x is away from the port as x, and distance that y is away from the port as y. How fast are the ships separating at 1 p.m. And let's notice that A left at 9 a.m. So A would have traveled from 9 a.m. to 1 p.m. So A goes for 4 hours, whereas B, because B left at 11 a.m., so 11 a.m. to 1 p.m., B travels for 2 hours. So that'll be important as we set up the problem. So what's given, what's the goal, and what's the equation that relates the variables? Typical things that we do when we set up our related rates examples. So the given is the rate of change of A and B, right? So dx dt is given, and it's positive because this distance keeps getting larger and larger as A moves away from the port. So dx dt is 12 and dy dt is 15. And we want to know how fast they are separating, so that's the direct distance between them. So at any moment, maybe A is over here, maybe B is over there. If I look at direct distance between them, that's what I'm calling Z to be. So they want to know at what rate is that distance changing. So that's dz dt. Find dz dt. And that should be positive as well. It's getting larger and larger as they move away from the port. At the moment when x is equal to something, y is equal to something. So this is what was not given to us explicitly, but we can figure it out. Since A has traveled for, based on the time at 1 p.m., right? They want to know this information. So at that time, A has traveled 4 hours. So 4 times 12 will be 48. So A has traveled for 48 miles. So at the moment when x is 48 and y equals, remember y has traveled 2 hours by 1 p.m. So 2 times 15 is 30, so y would have traveled 30 miles over that time period. So they want to know then what is dz dt at the moment when x is 48 and y is 30. Okay, from this point forward, this problem will be a pretty straightforward question to solve. Again, use your Pythagorean equation, x squared plus y squared equals z squared, and differentiate both sides, plug in the whatever is given, and solve for dz dt. At that point, you're also going to have to figure out z, and you can put the 48 in here, 30 in here, get z as well. And then after you differentiate both sides, you'll be able to plug in everything that is given, including z, and solve for dz dt. So for this one, I'm just going to give you the answer and leave it with that and have you finish the problem. dz dt should be 18.13 miles per hour. All right, the next question we'll do together. A similar problem, so let me give you a few moments to read the question first. Okay, so I'm hoping you took a moment to pause the video, read the question, and get the problem started a little bit at least. That way you can really learn it so much better when we go over it together. So ship A starts 40 miles north of B. So in the beginning, this entire distance was 40 miles, and it's going south at a rate of 15 miles per hour. Ship A is moving south. And ship B is traveling east at a rate of 12 miles per hour. The question is, how fast are the ships separating at 2 p.m.? So the direct distance between them. So if this is going that way, this is going that way at any given moment in time. Again, maybe one is this way, one is that way. So what is that direct distance z? At what rate is that distance changing? So again, we have a right triangle situation, so don't be surprised if we resort to using the Pythagorean theorem again. But let's start by again writing what's given, what's the goal as a derivative. So given dy dt, that's the rate of change, but notice that distance is getting smaller over time, so dy dt will be negative 15 miles per hour, whereas dx dt, that distance is getting larger over time, that's positive 12 miles per hour. And the goal is to find dz dt, the direct distance between them. dz dt equals to what? And at the moment when x equals, well, notice that they both started at noon, and we want to know what happens at 2 p.m. So they both traveled for 2 hours. So at that moment in time, how far has B traveled during the 2 hours? So 12 miles per hour multiplied by 2 in 2 hours, that one has traveled 24 miles. Okay, so x equals 24 miles. Okay, the y is a bit of a trick here. So remember that initially it started 40 miles away. 40 miles away, and he traveled for 2 hours south at a rate of 15 miles per hour, right? So how far did it move? 30 miles, right? 2 times 15 is 30. So it came down by 30. So at that moment in time, how far away is that one from the intersection? So it is 10 miles away from the intersection, right? So that then we're going to say that y is equal to 10. Okay, so that was a tricky part. But once you figure it out, the rest will be very similar to our typical distance rate problems. So y is equal to 10 miles. And the equation that relates the variables is your typical x squared plus y squared equals z squared. And what do you do with that? You differentiate with respect to time on both sides, cancel out the 2's, and then start plugging in what was given. So x is 24. This is given. dx dt is 12. Y is 10. And dy dt is negative 15. So I'm going to go ahead and put those values in. But then what do you do with the right hand side? We don't know yet. We do not yet know z, although we know dz dt is okay not to know because we're going to solve for that, but we don't know what z is. But if you have x and y, you can figure out z using the same equation, x squared plus y squared equals z squared. At the moment when x is this and y is that, we can use that equation to figure out our z. So I created a very simple triangle here showing that, okay, we have a right triangle situation. The vertical side is 10, the horizontal side is 24, and the hypotenuse is z. So we can write that 10 squared plus 24 squared equals z squared. From there we can solve for z, which is the square root of 10 squared plus 24 squared. So it turns out that z is 26, and once you find that, you will be able to come back and plug in here in your equation up here for z is 26, and at that point the only unknown is dz dt, and we can figure that out. And if you combine these numbers on the left, 24 times 12 minus 150, right, 10 times 15, you should be getting 138, and then divide both sides by 26 to get dz dt. So 138 divided by 26, and there we get approximately 5.3 miles per hour. So the rate at which the distance between the two of them is changing is 5.3 miles per hour. Okay, we're going to solve one more example in this segment, and this one is going to be a ladder problem. Another typical question in related rate sections. So in this situation, we have a ladder leaning against a wall, and the length of the ladder is 20 feet. The base of the ladder is being pulled away from the wall at a rate of 1 foot per second. So in this figure, I represented the distance of the ladder from the bottom to the corner of the wall as x. So it's being pulled away from the wall at a rate of 1 foot per second. So basically they're giving us dx dt here. dx dt is 1 foot per second. The question is, how fast is the top of the ladder moving down when the base of the ladder is 8 feet from the wall? So how fast is the top of the ladder moving? So they want to know basically the rate at which this top is coming down, which is dy over dt. And notice here, I did not put a z on the third side, on the hypotenuse. Instead, I put 20. That's the length of the ladder. Any thoughts on why I did that? Why didn't I put the z and started plugging that number in right away from the beginning? And you may have guessed it right. Unlike the distance rate problems where z was changing also over time, here the length of the ladder does not change over time. It's the same ladder that's sliding down, so no matter which position it's at, that hypotenuse will always be 20, right? So that doesn't change over time. The length of the ladder is a constant with respect to time. So it's okay to put that number in there right away. Actually, it's better so you don't complicate the problem by introducing an unnecessary variable. Okay? So the goal is, how fast is the top of the ladder moving? Oh, let's see. Why did I write that there? Interesting. Okay, so the ladder is the length of the ladder is 20. Sorry about that. So the question is, what is dy dt? That was the unknown. And the length of the ladder is 20. That's a constant. And dx dt is 1. So that's the question pretty much. So find the goal, find dy dt. And that's at the moment when the base of the ladder is 8 feet from the wall. So at the moment when x is equal to 8. What is given? Dx dt is 1. That's one of the given quantities. Dx dt is 1. And an equation that relates to variables. At any given moment as it's sliding, we're going to have a right triangle situation. And therefore, we can say x squared plus y squared equals 20 squared. Or 400. And typically, if we know dx dt and we're trying to get dy dt, we need to differentiate both sides of this equation with respect to the time variable. So we've done things like that before. 2x dx dt plus 2y dy dt equals 0, right? Derivative of a constant is 0. And you can divide both sides of the equation by 2. 0 over 2 is still 0, so the 2's are gone. And now you have a simpler version of your equation in which we can plug in the constants that we know. So x is 8. It's going to come in here. Dx dt is 1 right in here. Dy dt is unknown. It's okay to keep it as unknown at the moment. But we're going to need to find what y is at the given moment in time when x is 8. So that I did on the side over here to figure out the value of y. So we don't know what y is, but x is 8 and the length of the ladder is 20. So this is where you can go back to this equation, right? And you can figure out y because that was not given to us. So using the Pythagorean theorem, so x squared, which in our case is going to be 8. So 8 squared plus y squared equals 20 squared. And from there you can solve for y. So I can write it as 8 squared plus y squared equals 20 squared. At this point, subtract 8 squared from both sides and then take a square root. And you will have the following. Y equals the square root of 20 squared, which is 400, minus 8 squared, which is 64. So y equals the square root of 336. So now that we also know this quantity, we can go back and solve for dy dt. So again, dx dt was 1, x was 8, y we just got square root of 336, and dy dt is yet to be determined. So all we have to do is go ahead and subtract 8 from both sides and then divide by root 336. So first I subtract 8 and then I divide. So dy dt turns out to be negative 8 over the square root of 336. And if you get a decimal for that, you will get roughly negative 0.44. And units for y are feet and units for time are seconds. So feet per seconds. And it shouldn't surprise us that dy dt turned out to be negative because again, we see that that quantity gets smaller and smaller over time. Okay, we're going to solve another problem related to this in the next segment. As a matter of fact, we're going to figure out the rate of change of the angle, whether it's this angle or that top angle. So that'll be one of our first rate of change of angle problems. But I hope you feel more confident solving the rate of change of distance problems. And now it would be a great idea to go and solve a few different problems of those types to get a firm understanding of that specific type of problem. See you next time.